We're gonna warm up with some Rust brain teasers and just kind of get our brains going. And today's theme is underlying data representations. So put on your data representation hat. So here is a fun first one, and I want to see who can get closest to the right answer here. So we have a string called emoji, and it's this woman with a heart in between her and a man. And we are going to print out the emoji and call .len on it. So what do we think .len is going to print out here? Any guesses?
Should be the number of, to say it out loud, or
Yeah.
should be the number of UTF-8 characters within that. But then UTF-8 can do some weird things where, I don't know, you can mess with character widths, and so
right. Because we have
maybe that one character.
Because what we have 3 glyphs plus 2 joiners. Is that 3 put together?
Yeah, that's what I'm thinking.
Yep. So yeah, we've got some crowd out here talking about the number of characters, the number of glyphs. Anyone want to?
I'm just gonna say whatever it does, it's gonna lie because it's saying characters long. So.
I think a lot of the emojis are up in the 4 characters.
So we've got 3, we've got 4.
I like to think it's least surprising, so I want to say 1.
I'm going with 5.
28.
Not
all
what I
right.
was
So
going
what the heck is going on under the hood here?
Unicode magic.
Unicode magic is correct. Let me try to get this out of the.
You've added colors. Okay.
So what's cool, and some people have mentioned this, is that emoji is actually a combination of a bunch of other emojis. So it's like the woman, and then a white woman, and then white actually takes up. This is we'll get into the actual bytes afterwards, but like then there's a heart in between them. There's a man, and then there's the brown emoji. And so if you look at under the hood in Rust. Basically a string is kind of like a struct of bytes, right? And then if you look at a more basic string here of like hello timer, I don't even know what language that is, but you have this special O here. And so each one of these characters take up 1 byte, but that special one takes up 2. So if you were going to print them like 1 by 1, if you just iterated over, it would be like the first byte is H, the second is A. And so this was actually 28 because each one of these could be more than 1 as well here. So if you never looked under the hood of emojis, it's kind of fun. And I think some programs like Google Sheets, for example, if you put in that multiple people and you hit delete, it'll start like deleting people from the emoji until you get back to the first character there.
It's also really fun when you add too many of them and then it starts like trying to do a hyphenation and some of them just disappear.
That's hilarious.
Yeah, I know they had that security vulnerability related to like being able to hide text within source code.
Yeah, so I don't know if you guys could hear that, but he was talking about security vulnerability of hiding. What were you hiding?
You could hide actual code, but then use like these tricks in Unicode to where you could actually make it to where like if you open it in a UTF-8 compatible reader, then like you could actually see actual code that's not accurate, or that like you wouldn't see code that's actually there.
Wow.
And yeah, that was
some trip with backspaces.
Something like that. And yeah, the Rusty was actually as soon as that came out, then like Rusty actually had already passed it to where it'll refuse to compile if those are in unless you like override or something like that. I can't remember. And then VS Code also had it would inject its own warning in there.
That's awesome. I mean, scary, but awesome at the same time. Cool. So some more sizing. Here we have a struct, and it's a very important message, and it has a message type that's a U8 and a destination that's a U16. So we're just going to print out the size of this very important message. Any guesses on the size here?
You might have alignments.
32.
Yeah.
Round up.
Sort of things, right?
Platform?
Your two core processor, you might be out of.
Yep, so we have a lot of guesses around 32.
Doesn't Rust see like unlike C, it'll actually optimize the structs and not necessarily unless you like put a attribute to say
True.
rep C or something like that.
Yep, all along the right lines here.
Oh,
So very important
Four.
message will occupy 4
bytes.
bytes.
Yeah.
32 bits. But it feels like it should be 3, right? Because we have the U8 and the U16. And so what Rust does to align to modern CPUs on the 32-bit boundaries, they will pad these structs. And so this can be sneaky and this can bite you, is what I had there.
Wah, wah, wah.
Only to bite you on the FF5, right? Or not?
Yes, yep. Yeah, it's just hard because I can't see my mouse. So anyways, this will bite you if you have like a foreign function interface and you're trying to integrate like C and Rust. So to your point, there are some macros that you can put in here of repr C and packed if you like really wanted it to be 3 bytes for your use case.
Oh,
All right, here is another fun one, and this will take some knowing what all of these, what is an option, what is an RC, what is a ref cell. They define a struct that's just a node, and they're building a linked list here. And so the question is, what is the output of this going to be? So we have head here, where we put an RC new RC ref cell, and then one node, which is has the element of 1 and no next value. We turn it to mute, we unwrap it, we borrow the mute, we set next to a new RC ref cell with element 2 and clone the head. What is going to happen here?
ooh, okay.
Is that gonna leak?
It's not good, that's for sure.
Well, because ref cell, like, I haven't used it much, but as far as I know, it's it does its own reference counting, doesn't it? And then
Yep.
adding the RC on top of it to reference count again.
Yep,
We made a
so
lovely circle. Okay.
a lovely circle. Yes, we're on the right track there. So RC provides reference counting. And so as it gets instantiated, the reference count will go up by 1. And then ref cell provides a mutable memory location that makes borrow checking dynamic rather than static. So when you borrow the contents of a rest cell, Rust notes that the borrow has occurred at runtime rather than compile time. So this will actually is really nice for making linked lists in Rust, but in this case will overflow and just put you in an infinite loop because we just tied the front to the back and we weren't able to catch it at compile time like you can with other data structures within Rust. So powerful, but dangerous as well.
And if we hadn't printed it, we would have been okay.
If we hadn't printed it, we would have been okay. You want to elaborate on that?
Well, I mean, when we tried to print it and then it just, kept trying to walk its way through, but we had a data structure that was probably okay if we, were very careful in how we used it, like we were C programmers. And but it is frustrating when debug or print is what destroys your or demonstrates what doesn't work about your code. Yeah.
Exactly. So he said we would have been fine if we didn't print it. It's frustrating when print starts to unwrap the data structure that you have under the hood. So it's like my code worked until I tried to debug it with a print line and then everything crashes. What is happening? So that's a fun one too. Cool. So enough brain teasers. I limited it to 3, but I hope you guys like that as kind of like kicking off. There's actually a whole book of these that I grabbed it from. So we can have a good amount of these for next meetups too, if we want.
Really, where's that come from?
It is from this book called Rust Brain Teasers. Exercise your mind. Pragmatic programmers, and there's a bunch of different puzzles in here. So I just grabbed a couple of random ones. Cool. Cool. So who are we? We're Oxen AI. I'm the CEO and technical founder. I come from a machine learning background and working with massive machine learning data sets. And I, throughout my career, always wished that there was like a version control tool that could work natively with these data types and for the scale and size of data that we were working with here. So for example, like when I was working on a computer vision project, I wish I could just add the images directory, add all the big binary Parquet files, commit them and push them, and have that be super fast, super efficient on disk. If I add one image or add one row to a Parquet file, I don't want that to like balloon my storage or make me transfer all of that data again. So what we've done is built a command line tool and a Python interface that has all of those properties. And then we have a web hub that's kind of like GitHub, but optimized for data sets rather than optimized for code. So they kind of have different shapes there. And so we have a couple projects on GitHub. We have like the Oxen core, which is all written in Rust, and that's a command line tool, a library, and a server. So the command line tool talks to the server and is connected through the library. And then we have a Python library that sits on top of that, that uses the Rust core internally, and is just like very lightweight wrappers on top of it. And lots of people in the machine learning community use Python and not Rust, but all of the core within there is Rust. And so why are we building it? Obviously AI is getting bigger and bigger today, but when you break it down, like AI is pretty much just code that's been put with data, and then you get a model out the other side. And we have really good tools for collaborating on and iterating on code, not great tools for collaborating and iterating on the data sets that go in to train these models. And as AI is getting into the hands of more and more software engineers, you start to add this like non-deterministic inputs and outputs, and like really opening up the scope of what's coming in and out of your model. So all the more reason for a version control tool to help you with it. And so there's some extensions to Git. You might have heard of Git LFS to try to handle some of these larger files. And what it'll do is allow you to just like hash the file, put the pointer into your Git repo, and then just like version the pointers. And Git's really great for like a bunch of small text files, and they do some cool things with pack files and diffs under the hood. But even from the documentation, they say Git works with reasonably sized repos with infrequent updates. And if you look at some of these things that go to train machine learning models, like ImageNet, which was a big data set back in like 2013, 2013 is like 14 million images. And this is like a small data set in terms of machine learning data sets today. GitLFS also maxes out some of the file limits, and it's just like painfully slow to work with if you've ever worked with it before. So just some like high level benchmarks, Oxen versus there's another tool called DVC, and then GitLFS. If you just went and added, committed, and pushed 100,000 images, Oxen does that in a few minutes, and GitLFS on the same AWS network took like 2 hours, right? So from like a developer iteration speed time, this is super frustrating. This starts to get into, okay, we can start collaborating together. And so optimizing for a few different things. Like I said, like you might have a repository of many small files like ImageNet, a bunch of JPEGs in a bunch of different directories. We might have a few large files. There's like smaller training data sets or fine-tuning data sets that are coming out today that might just be like a CSV with 100,000 rows in it or something like that. So like a 1 gigabyte CSV of text that's going into your model. Or you might have many large files, which is if you look at any of the data sets that go to train the foundation models, like the models before ChatGPT, that might be like 45 terabytes of text data split out and sharded over a bunch of binary Parquet files. And so this is like the extreme case of those two. So those are the three types of data that we're optimizing for. And so why Rust is we can go all the way down and optimize to the byte level if we want. We can minimize the copying as we're going through this whole process. We want to be able to perform search, read, writes, and fast network transfer in parallel. So like the fearless concurrency that Rust brings you is really valuable there. And all of these small optimizations lead to the big performance gains that you get between like a tool that wasn't built for the scale of data and a tool that was. So I'm documenting a lot of this stuff as I go along, and I'm putting it into this Oxen AI book, which I hope is helpful for like the open source community. So what was the URL? oxenai.github.io. And so everything down to like how to build, run, contribute to like the data models that we have under the hood, how things are stored on disk, all that kind of stuff. So that one, new engineers can come into our team and collaborate better, but like it is an open source project that I would love more people to dive into. And so what I wanted to do was like start by how we could build a naive version control system in like 5 minutes. It's actually not that hard once you break down these fundamentals. And then we'll see how Oxen Merkel trees under the hood help us scale up to many files or large files that change over time. So how does version control work under the hood? If you've never like looked in your .git directory, this is going to be a TLDR on that. So you have like your working directory that might look like this, where you have a README, a license, and a bunch of images. You might init, add, commit. And if you look on disk, there's going to be like a hidden directory. In our case, we call it .oxen. In Git's case, it's called .git. And within there, in our case, we have a /versions/files directory, and you'll see all of these crazy hashes and then some data files that live underneath there. So what this is a content addressable file system where we take the hash of the data. The hash of that JPEG would be like 4394F whatever. And we store that there so that if you have the same file over multiple commits, we only store it once. And as long as we have the hash, we can immediately get back to it. And so naively, what you might want to do is you take all of the hashes of all of the files within that commit, and you hash all of them to get a commit ID that is like the verifiable contents of all of the data within that commit. So what that might look like under the hood is you might have like a key value database of like all of the file names to their hashes and maybe some other metadata about them, right? And then if you want to like switch between commits, now you have a database per commit with all of the hashes of all of the content, and you could just like naively clear your working directory, go into this versions directory that you've saved off copies of all the data and restore them all to their original format because you have like every single file that was within that commit with their hashes that you can come back, grab the original data and restore it to its original place. So that would be like a super naive version control system. Everybody following so far? Any questions? Cool. So now we can just call it a day and go relax on the beach. We've done version control. Except not. So the content addressable file system is great, but the key value store per commit is not. So let's imagine that we had like commit A that had 3 images, and then commit B, we add 1 more image, and then commit C, we add 1 more image, and then et cetera, until we get to like 10,000 commits where we just added 1 image each time. Now each one of these databases has exploded, right? So back of the napkin math, if you're just doing this and you had 100,000 images, each commit, you add 1 more. Now you have, after 4 commits, you have 400,000 entries in all of your databases. So like, if you blow that up over a giant commit history, that's not super efficient. So enter this data structure called a Merkel tree. And so our files and folders are already in a tree structure, right? So that's nice for 1. And then for 2, we're hashing all of this content. And those 2 combinations, pretty much of a tree structure and hashes, are what makes up a Merkel tree. So you'll have all these nodes at the bottom. I don't actually have their hashes, but they'll bubble up to a hash here. All of those hashes bubble up to another hash. All of those hashes bubble up to another hash. And now we have a tree-like data structure instead of this key value type store. And what's cool with that is, say we just want to update the README in our commit, and we're not touching anything down here in our images directory. All we really have to update is the nodes on that part of the tree all the way to the root. So if we had like 2 files within the root directory, README and license, and README gets updated, we're going to recompute the hash for README, recompute the hash for README plus license, and then compute the hash for the images directory plus the other files in there plus the root. You could also look at this all the way down to like the image directory level. And you might have noticed this already, but I have different buckets down here at the bottom of images. We call them V nodes internally. But like if you had 100,000 images in this directory and you just wanted to update or add 1 at the end, again, we don't want to have to copy all of those hashes and have pointers to all of them there. So we have these smaller configurable sized V nodes within each directory to shard these large directories and make the storage even more optimal there. So like, to concretely look at this, if we had a data set of 100,000 images, a license, and a README, the initial commit, we might add 100,000 pointers in there. The update the README, just 1 more, update the license, 2 more for the README and the license. Add another image, depending on the vnode size here. We have 3, but like in a more production use case, you might have like a vnode size of 10,000 or something like that. For those 4 commits, we've shrunk the storage from 400,000 entries to 100,000, 10, and 3. And you can imagine if you did like 100 commits, right? We're growing logarithmically instead of quadratically, which is really cool. And we share these nodes across commits. So it's kind of like a Merkel tree, but shared across versions, which is kind of cool. So that's great for many files, but what about large files? So large files, you still have at the base of this tree, you could have a giant CSV that's like 1 gigabyte, and then maybe you add 1 row to it at the end. So going 1 more deeper, maybe you have like 1 million rows in this CSV, and you just want to add 1 at the end. This is super common in like training data collection for these machine learning models. And it'd be great if we didn't have to store all of this 1 gigabyte and all of this 1.01 gigabyte in that version directory there. So we break down the data even farther, and at the leaf node there, it is no longer the leaf. And we can take these chunks and chunk it into like 16 kilobyte versions there. And then depending on how many chunks you have for the file, if you update that last row, now you just have to update the hash for that chunk of the file. And we have an even bigger tree where at the base we have chunks of the file instead of the files themselves. And then you update that one chunk. You only have to update those nodes. And then what's also cool from like a network transfer perspective is I don't have to go transfer a gigabyte. I only need to transfer that one chunk that got modified. And then we also need some pointers for like the order of the chunks, but that's all that's really stored at the bottom of the tree there. And so benefits here, minimize storage overhead. You copy only what you need both on disk and over the network. You can quickly validate the contents of your whole commit by just bubbling up the changes through the tree and making sure the hash is hashed to the hashes all the way to the top. And logarithms and trees are just fun in general to save you all of that work. So if you like working on this type of stuff, we're hiring as well, and like to get all the way down to the nitty-gritty details, byte level data structures, all that fun low-level optimization. So that's it. I had some ideas for future topics. I'm curious what you guys like about this format, if we want more guest lectures of that kind of stuff. We want to like dive into some open source code repositories and just like see how they're structured. I thought that could be cool. Or Phil talked about, they just did like some live programming together. So open for ideas there, but hope you guys liked it. Yeah.
Sorry, need to interrupt you. I was just thinking of this time, I went to like a Microsoft, I think it was also through Meetup, some kind of hacking, or not like malicious hacking, but just like in a good sense of the word. And they had a thing which was, the guy who was running it set up like an API endpoint, and the challenge was people were split into teams, and they could call the API endpoint to get information about an asteroid that was coming towards Earth, and then they had to like fire a railgun by submitting API calls.
Oh, wow.
And it was like you had to calculate the trajectory or something. Obviously, it's like wouldn't actually work in real life, but calculate the trajectory and then fire it so that it intersected the path. And I just found like that sort of format of there's something that you're doing that's engaging, that's like an active challenge. That there's maybe even a little bit of like a friendly competitive aspect too.
That's cool. Yeah.
Like that kind of stuff I really
I like that. Yeah. So yeah. Oh yeah. That's interesting. Yeah, so we're doing a climate kind of hackathon as a group where we're hacking on data. That could be an interesting theme to like have some practical real world thing that we're building together during the meetup too. Oh, cool. I like that. Any other thoughts or ideas or like ways that you guys would want to run this?
I'm not very good at presenting, but occasionally have people ask me how I got a Microsoft bug bounty, and it was actually using Rust.
Oh, cool.
Maybe I could show that someday.
Yeah. I mean, we love
I'm
just
just not very good at presenting. That's the only problem.
Hey, we don't need to be great. We just need to talk about some nerdy stuff. And your name is Nikolai, right? Yeah. So if you guys couldn't hear, he's building a video streaming and
I work at Paramount.
work at Paramount.
Yes. I'm leading advertising ad tech engineering team, but we're building like video streaming platforms, P+, Hulu TV, Showtime. If you heard, that's what we're doing.
Cool.
So I can share that experience with you. Like I'm running CVP media practice in Paramount related to Rust. But my team kind of brought the experience to the company. So yeah, excited to hear that there's Rust community in LA. So
love it. Yeah, and all of those learnings. I know I kept it kind of high level here, but even like pointing out whatever functions of Rust that you found super helpful.
Different use cases that really Rust just was perfect for us. I can do a lot of resource optimizations, cost savings, if you guys are interested to hear about these things.
Nice.
Would love to speak.
Love that. Yeah. Anybody online? Any things we could do better for the live stream? It's kind of flying by the seat of our pants here, but I hope we did a good job.
I recommend continuing to fly by the seat of the pants. It's very real and exciting. I ran the LA Pearl Mongers for 20 some odd years. And we found that sometimes we just have very low key ones where we just like, or especially, hey, somebody go learn to use some package and just come explain it to us.
Yeah.
Which then you are forced to learn it and then you show other people and we chat and it's fun. So that is a nice one for people who are like, oh, I'm not writing any code. Like I don't have a package. Go learn one and teach us. So
Cool.
thank you for presenting and stuff, by the way. I don't think we stopped for applause. That was fun.
Oh, yeah. Sure. Thank you. Appreciate it. All right, I'll give you this view. Look at this thing.
Great. Take this guy? Yeah.
Ooh.
All right, I think the recording's still going.
Okay. Greg, your presentation was amazing. And I have spent my entire career at the opposite end of the scale. So this is a device called a cozy, or at least this is the intelligence of donut. It's called a cozy. And the company I work for is named Kelvin. They're in Brooklyn. Anybody from New York? Has anybody lived with steam heat?
Yes.
Okay, so
Gurgle.
that is exactly where we're at. So the founder of our company, at the time when he came up with his brilliant idea, was going to school in New York, to Columbia, and work on his electrical engineering degree. And his brother got a part in a show. So he was going off to Broadway. You don't know how it's going to go, not making great money. So he was crashing his brother's dorm room while he's working on the show. And you got steam heat. And one of the things that happens in steam heat. So you've seen, those of you who haven't been in New York, you've seen those steam radiators in movies and whatever. And what happens is there's a boiler down on the bottom of the building, and it shoves steam up through pipes into these radiators. And there's only one control, right? The boiler is how hot it is. All the rooms get this radiator pumping heat into the room. And by law, you have to keep every room in your building above a certain threshold temperature. And if you don't, that person gets to stay with you without paying rent. So there's a motivation to keep the rooms warm. So you figure whatever the coldest room in the building is, and you're going to drive it a few degrees above that minimum threshold, which means every other room in the building is too hot. In some cases, much, much too hot. So there's places in New York where in the middle of winter, freezing temperatures, 2/3 of the windows in the building will be open. Because you have to. And what this does, interestingly, is the cold air coming out of the radiators then causes the steam to precipitate out as water, which means you actually have to force more heat in to drive up through this water raining down. And oh, by the way, since the water's so pure, it's actually corrosive and it's eating your pipes. I mean, your pipes break, it causes millions of dollars of damage to your building. It's a horror show. And everybody's miserable. And so the founder's brother, staying there with his show, I guess just pissed and moaned so much to his brother that the electrical engineer went, okay, I got to do something just to shut him up. And what he did was he built an insulating box for the radiator out of basically aluminum foil, took a little controller and a fan, and basically a couple temperature sensors, and used that to drive how much heat pushed out of the insulating box so they could set their temperature to whatever they want. And that's what we make. So we sell insulating enclosures at a building scale, and we collect data from every room in the building from the insulated sensor about how hot's your radiator, what's happening with these steam traps that collect to make sure you don't have water precipitating out, what's the room temperature. And this means that you can control the boiler to an optimum setting. So we're cutting power usage for the heating by 25 to 40%. which means cost goes down, which means carbon emissions go down, and we're making so everybody in the building can bloody well be comfortable, which is just a blessing, right? Instead of sweating your butt off and having your window open in the middle of winter, you can actually have it be the right temperature. So it's a wonderful plus for the people who live there too. And company's been around nearly 10 years. We're at a place where parts obsolescence has run the controllers that they were kind of building the business out of. They can fit our parts and stuff, so we've decided to build a new generation. And that's what this is. So in here is the Cozy controller. And you can see it's below embedded systems board. It's a 3-board stack here, the main controller board. There's a board for a display and there's a sensor board that sits here. On this is a microcontroller. The microcontroller, and Greg, this is like the exact opposite view, has 256K of flash, a 1/4 megabyte of flash. It has 64K of RAM and 1K of what's called double EEPROM, which is a fast write non-volatile storage. So flash is a lot harder to write. If you have like a black box that's going to say I'm crashing, I'm failing, you want to write it fast, you can't hit flash, so you go to double EEPROM. This has on the microcontroller a radio for a technology stack called LoRa. LoRa is a very low power. So if you're putting a sensor and you want to like, I'm going to measure the water table, you could put a sensor and a battery and a radio into like some field. And because if you only made it turn on maybe once an hour and transmit, hey, here's the water level, here's the water level. That might run for 10 years because the battery consumption of LoRa is so low. And it can transmit about 10 kilometers. So it's got pretty good range. Inside of New York, you get a lot smaller range. So we actually have maybe a gateway every couple stories inside of a building. But we can collect data off of every single one of these. And there's a data warehouse that we have that's constantly getting messages up. So this sends a message every 10 minutes that says, how hard are we driving? The fan. There might be 1 or 2 fans depending on the configuration. They get customized depending on the room that they're going into. And there's all these pins coming off here, which is normally at my home hooked up to test stands, so little boards that act like the sensors. But these are pulling off either the fans and the fan tachometers, sensors in the steam traps, sensors in the room. Yeah, the whole suite of sensors. So we pick all the data up and we send it off to home base every 10 minutes. There's some lower quality data that we send every 30 minutes, less volatile data. And they use that at the data warehouse to figure out how hot should we be driving the boiler. And also, are we seeing weird things? We can tell if we're seeing leaks of cold air coming into rooms based on this. We can tell if the steam traps are having problems and getting stuck and are going to cause damage from the water flow out. Just through this whole sort of data warehouse size. And so if you come around to the other side, this is the user interface, trivially simple because it's a heating controller, right? It doesn't do a whole lot. You've got what the temperature is. It's 77 degrees in here. There's right here a little thermopile. So this is taking an IR reading way out, so it's reading somewhere out in that area. If I put my hand in front of it, it'll get warmer faster. And so the temperature, 79 with my hand in front of it. And then if I touch it, it'll illuminate. Why is it not illuminate? You see the tape around here? I'm actually debugging a physical problem with the touch panel, and I wonder if I've actually managed to cause it.
I feel like it's light up before. I saw it.
It's capacitive. We have a problem right now that we're debugging where the frame of the touch panel will touch the metal frame here. And if it touches it just right, the thing thinks it's being touched all the time. And you can't, so I'm actually working with a hardware engineer to try and solve that right now. So I'm going to turn it off. It says power loss, so it wasn't completely dead, but the touch panel is dead. And I have to wait, there's a little red light back here because there's a supercapacitor on this. And what we want to know is when somebody unplugs one of these, we want to know that it happened. Because like they'll unplug it during the summertime when it's not heating season. And then heating season, I'm like, why is my room cold? And nothing plugged in. And so we can actually tell that with this. Because with the supercapacitor, as soon as I sense the power's off, I, over the LoRa radio, send a message off that say, hey, I've lost power. And we give them this little message on the screen that says, hey, I've lost power, but I have to wait like a minute and a half before this sewer cap will discharge before I can turn it on again and we'll reset the touch band. But anyways, when the thing senses a set point, you know, I'm sitting here saying I want whatever 75 degrees. When we're below that temperature, it will run the fan to try and drive heat into the room. And there's some additional things that it's usually looking at. If I have it hooked up right, it'll be looking at the temperature sensors in the radiator, say, are we actually going to push hot air in because the radiator is hot enough or not? And then this is just a simple fan you control with a pulse width modulation signal. And so just depending on how we adjust a little square wave and depending on how much up versus down it is, that controls how fast the fan will go. At full speed, it's about a 5,000 RPM fan, so it's not terribly fast. This whole thing is kind of an interesting system because it's very slow. So I've spent most of my career doing devices where you're controlling between 500 and 10,000 times per second. On this, I'm controlling every second and a half. So it's a completely different scale because temperature just doesn't change that fast.
What were the things you were working on before?
Medical ventilators, surgical devices, all kinds of, lots of safety critical and lots of high reliability, long uptime storage devices.
So how does one program in Rust on there?
So when programs in Rust, where I have back here, this is a debug probe. And we're hooked in through a communication signal called JTAG. And JTAG's been around forever and ever, and it lets you touch into the microcontroller. So I hook up my USB to my Mac here, if I pull it open, and let's do that. This is an ST Micro ARM M4 Plus. The processor actually has both an M4 core and an M0 core that it can use for security. An M0 is a very, very tiny microcontroller. Like usually those things are running around with like 8K of RAM and 24K of flash. They're really, really tiny. And that's just used for security and starting the radio up in some high security applications. We actually turn it off, but it turns out that you can get this processor with and without the M0 core, but they make like 100 times more of the slightly more expensive Hacking 2 core ones, so we buy it just because of availability.
Is it 8-bit?
I'm sorry?
8-bit?
No, they're all 32. They're
Oh, really?
Yeah. So these are ST Micro implementations. They are ST Micro probably has the best Rust support in embedded. So them and the folks that make the NRF parts. I'm drawing a blank on their name. There's two brands that have really good general support, and there's a lot of stuff that has kind of medium support. It's only kind of growing slowly on what you want to work on. But ST Micro makes they have a lot of advantages. Their processors are around forever. So like they have not discontinued a processor in the STM32 family. So from whatever 20 years ago, you can still get that part today. And an embedded system, that's really important, right? An embedded system cycle, you're typically building something for 8 to 10 years. So you want parts that are going to stay around a long, long time.
We use a lot of their stuff.
Okay, so most of the things I do through the span line here. So if I off on again. Most of the code I'll write in VS Code. And then just through cargo, you've got some commands of, there's a whole set of stuff from a library called probe.rs that knows how to talk to the debug probes and can program the device and can hook up to debuggers. So you can do source level debugging, do all the kind of fast work on this. So if I come in here and I say cargo XT short for XTask, which is a
We crowd around here.
yeah. If I tell it flash here, it's going to go here and rebuild the source. And right now it's erasing the flashing device. Now it's programming the flashing device. And it comes up here and tells me, hey, my program's starting on. This is just a debug text interface. At the same time, I have a second channel that's going over this that's used for testing data. So if I I'll break out of that. And I'm going to say console, and console's going to listen to the other channel. Oh, well, it builds and toss that up. And now it's giving me message number 2326. S is the number of startup counts. This thing right here is the error message that's coming off. So the 2 at the end here tells me I've had a crash at some point that I need to go grab the data from. The 8 there up in the middle tells me that I don't have the a couple of sensors plugged in. And then the states here, not joined, that's the LoRa. So it's trying to find a LoRa protocol it can talk to, but it can't. And then watchdog reset is why we crashed back in whenever. And then none is the state of the touch. And then this last thing, this and max, is I'm collecting some data on the jitter of the signal. So how fast do I get a message? I'm supposed to get a message off this thing to the debug channel every second. This console is here to let me do hardware in loop testing. So I can go in the backside and listen to what's happening. And then when I have this fully set up, and I've pulled things off because for transport, I didn't want to do it. But I have individual microcontroller boards that are hooked up to all the sensors that will simulate all the sensors. So I can have it simulate the tachometer inputs. I can have it simulate all the sensors. The sensors are mostly just voltage levels. And so you can set up, I've got this way too high, I've got this way too low. And you just build all your test suite off that. I've got a set of commands that I can just execute and it'll automate all the testing. I have a second set of this. This is my regular development one that I'm typing code into. There's another one that's sitting in the garage that's just headless, hooked up to a GitHub Actions. So every time code pushes, it goes and runs an hour's worth of testing.
Cool.
And then now if you see me touching, it'll show where the touch inputs were as part of the console data.
Yeah.
And there's a ton more data. I actually go and change that program every once in a while to show what the data is coming off, just for what I'm interested in at the time. And now if I change the set point, I need to go up a little ways. We're now pushing warm air into the room.
Physical testing.
Love it.
It's different. It's cool because you actually get to see something happening and you got a physical interaction.
Yeah.
Everyone's like, why's the fan? You hear things, which you don't get to do in a lot of other parts of computing. So anyways, that's kind of just embedded systems development. I do VS Code's my normal tool. VS Code, the source level debugger inputs work with this. So I can go in and single step through the code. I can inspect memory. I can do all the things you do with any other kind of program. I have the clippy linters turned way the heck up because my expectation is this device's uptime is months or years. So using Rust is one of those things that makes me a little bit more confident that I can actually start achieving those kind of uptimes on a device. So yeah.
What happens when it panics?
What happens when it panics? It does have panics, right? And I've got a panic handler that is custom built, and the panic handler goes and writes a number of things to the EE prompt. So remember where I showed in here where it says, first it's got the 2 at the end of the status number, and it over here says watchdog reset. Well, I had a watchdog reset, and the watchdog on a microcontroller like this is a piece of hardware that you configure, and it says in this case, it's about 10 seconds. If you don't go and write to a register in a specific manner every 10 seconds, it just resets the processor. Just pulls the reset line down, comes back up. And if that happens, there's another register that tells me the status of why your computer's starting up, and I can go read and say, I had a watchdog reset. And then I record that, and then the status bit tells the data center to pick up that data, and it will send it back to me to say, hey, you've had a failure in the field. And then any of the panics similarly go and write keep the process counter and a couple of other items of data that collected during the panic. Because of the size of this, like I say, there's a quarter mega of flash in there. I can't keep all the normal panic data. So there's an option in the way you build that basically strips all the panic data out, which is unfortunate. You don't get those beautiful messages. You have to hunt back and look at what source line of code that was. And so you keep good version control, make sure you've always written, you know, the exact version you have out, so you can backtrack and figure out what caused you to crash.
Very cool. We have a question coming. Thanks for drawing attention to it. Did the microcontroller require custom work on your side to support?
No. No, there's a whole community for embedded systems, a working group as part of the Rust community. And they have this particular microcontroller, the SM30 family, is very well supported. There are things we had to do. This has this LoRa radio on it, and the LoRa radio support is young and not quite where we need it. So they did most of the basic stuff, but for example, they didn't do what's called Class C communications. Class A communications is a basic, and that's meant where essentially when the radio on the device sends a message, the gateway, if it has anything to send, waits until it receives a message, and there's a short period, fraction of a second, where you can send a message back. And then after that, the radio shuts down, and it won't operate until the next time the device decides it has a message to send. So it's hard to get information down to that. We're plugged into a wall. We don't have that sort of power restrictions, so we can use what's called Class C, and at Class C, we can take unsolicited messages from the gateway. That was not supported in the LoRa Rust drive. So we found part of the LoRa Rust community, and we hired them on a contract basis to go add that feature, which is now in the open source LoRa.rs. Well, we've actually made a number of drivers ourselves for parts that were specific to our board, and those are all released in the open source community. We're also contracting the RS people to add multicast support, and we worked with another company on adding firmware update over the air support. And the LoRa firmware update over the air is pretty interesting stuff. It is it's designed where you can update a bunch of devices simultaneously. So you send all the messages out to these ones and say, here, get ready to listen, get ready to listen, get ready to listen, get ready to listen. And then you just stream packet after packet. And the packets have forward error correction in them. So if you miss packets, it can figure it out and reassemble. And you don't have to be sending messages back up to the server to say, hey, I missed package number 45 or whatever. It uses a technique called Gaussian elimination, which does a bunch of fancy XORs and such to rebuild the data. And so we think with the algorithm that we're bringing right now, we're going to get up to be able to sustain a send with 45% higher. So, and then you get a full update out of it. Now the updates are slow. Like LoRa's a long range, low power, it ain't fast. So updating that 1/4 meg of flash will take 6 to 8 hours.
Yeah. So what does it mean for microprocessor to support Rust? So it's basically a driver, you said. Basically, driver has to arrive a certain type of microprocessor in order to start work with Rust.
Yeah, so there's a bootstrap that goes and writes all the initial configurations of the microcontroller. And then there's drivers for many or all, depending on which processor, of the different sort of registries within a system, right? A microcontroller like this has, like, it has a bunch of ADD converters, the DA converters, it's got a PWM, it's got tachometers that are all inherent, and they have their own little API based on registers. And that may or may not be supported on the processor you're going to. As I say, this one is fairly well supported, and there's sort of two big camps of how it works. And there's the core embedded Rust, which makes no assumption about what you've got layered on top of it. Yeah. And so you might just put bare metal. You might put a microkernel, like a real-time microkernel like Arctic onto it. And there's also something called Embassy. And Embassy is a set of libraries that implement the async protocols. So you can use the async await approaches with them, which, depending on what you're doing, can make sense or might not. I'm using Embassy on this. The LoRa RS is built around Embassy, so it kind of was a forcing function. Embassy is probably only appropriate for a soft real-time application, right? And have you guys, that a new term? I'll explain. So a real-time system expects that you're going to be able to serve something in a certain amount of time. A hard real-time system says if you don't get it in that amount of time, it is a bug, and often a serious bug. So when I was making medical ventilators, if you missed a time window, you reset the vent. Now, it restarted in a fraction of a second, it could start delivering air to the patient in that fraction of a second. It would also immediately begin alarming and tell them, go replace this thing, it's broken. That's a hard real-time system. This is a soft real-time system. If I miss a window, who cares? You know, as long as I'm most of the time good with it, like I said, temperature doesn't change that fast, the fan doesn't move that quick. So it's a soft real-time system in this one makes sense with Embassy and async await. Async await just doesn't give you the control of time. And in a hard real-time system, you'd work a very different way.
Got it. Cool.
So
How much would it,
just
how much is it, sorry, I was gonna ask like how much.
I'm sorry, I didn't quite hear that.
Sorry, I was gonna ask how much does it take, how much will like a starter development board for this ST microcontroller cost? Like usually you want to.
Oh, so first off, if you buy any development board, if you go and buy, like the development board for this processor will cost you about $18. It has a source code order on it. Right? It has the hardware ST-Link chip just sitting right there. You can buy a standalone one. I gotta think. I think the education discounts are like in the $30 range. And I think buying one commercial is 100, 150 without the, but they're pretty generous with what the education ones. But seriously, just buy a dev board. And if you want recommendations, send me a note on the chat, and I'll get to it when I get home and send you a couple recommendations. There's a couple of teams, consultancies for embedded systems who have made training and they're built around specific boards. And so you may want to, you know, I'm going to do training, so I'm going to get, you know, they're using this NRF32 board that has, you know, a Wi-Fi and a this on it, and we're going to go learn how to do Wi-Fi and USB controls. So you need a processor that has that sort of.
Thanks for
That
joining,
was super
guys.
fun. Thank you for joining, for sharing that. That was cool.
Yeah, I wish I could be there. Couldn't get there.
Yeah, we'll let me check. Yeah, we'll do another of these soon. So yeah, if anyone wants to be in person, that'd be great. And we'll keep zooming them just to make sure we get people wherever they are.
That's good.
Thanks for including us.
Thanks.
And send out some Oxen docs. That was fun.
Oh yeah, yeah, that's a good idea. I'll send out a little follow-up for everyone. And then yeah, please send if you have more ideas or if you ever want to present anything. Would love to just keep doing it. We just trying to encourage people to demo and have a little fun.
All righty.
Awesome. Thanks, guys.
Thank you.
Thanks.
Bye.
Keep it rusty.